A very good evening, all. Welcome to problem solving session number 7 of the course Mechanics of Material. So, this week we are going to see how to solve problems of flexural members. So, last week we would have seen problems for axial members. So, this week mainly the assignment focus on flexural members. Okay. So before going to the problem, let me quickly recap some of the important concepts required in order to solve a problem. Quickly summarizing the content of the lectures. So flexural members are members which are subjected to transverse loading, which make them bend. Right? Say suppose if we have a beam like this, and say if this is my xyz, x y and z coordinate, and if I have a loading in the plane, in plane loading like this, some loading, so I can write my stress tensor as sigma is equal to sigma xx, sigma xy, sigma xz, sigma again xy is symmetric, sigma yy, sigma yz, sigma xz, sigma yz, sigma z. So this is my stress tensor, and we know traction at some plane Ex is given by sigma transpose times Ex, right? So this can will give rise to sigma xx Ex plus sigma xy Ey plus sigma xz Ez. Right. So this is traction along Ex. Now, if I want to find a net force, I need to do integration of this traction over the cross surface area, right? Area dA. dA is nothing but here I am taking an area which is perpendicular to x-axis. So dA will be dy and dz. So this will give rise to three force components, that is axial force along x direction and the two forces along y and z direction. They are called shear force along y direction and shear force along z direction, right? So this is my force vector, right? So this P is nothing but the axial force. So sigma xx dA, right? And this Vy is nothing but the shear force, which is sigma xy dA, and this is sigma xz dA, right, over the cross section area. Fine, this is the force along the section. Next moment along the section, so we got three force component, and similarly we will get three moment component. Let's see what are they. This is nothing but r cross f. F is the traction. So traction vector along Ex I'm taking, so dA. So this, if you further simplify, further we would have got Tx plus My minus Vz x naught Ey. By the way, this x naught is nothing but suppose if I am cutting a section, say at x naught distance from the support, from my origin, this is x naught. Okay, right, this is the origin. Maybe you can take x start from here. And finally, mz plus vy x naught. Okay, I'm just writing the final step so you can watch the lectures for uh, particular steps. Now, this will give rise to the following equilibrium equation. If you put summation of Fi equal to 0, we will get d. These are the equilibrium equations which will help us to solve the boundary value problem. So that is dvy by dx plus qy is equal to 0. This is coming from force equilibrium. Also, dmz, moment about z, the bending moment about z axis, by dx plus vy is equal to 0. Okay, see, these two are the equilibrium equations. So apart from that, we can actually combine these two in order to get the third equation, that is d square mz by dx square will be qy. Fine, right. Now, also we would have seen the relationship between the flexural rigidity, the radius of curvature, the bending equation, right? The bending equation. So the bending equation is minus sigma xx, the bending normal stress, divided by y minus y naught. Y naught is the distance from the neutral axis. Y is the layer distance, right? Equal to mg by IZZ. IZZ is the moment of inertia about the ZZ axis, centroid, right? E by R. 1 by R is curvature, so this will be d square delta y by dx square. Okay, so this was the bending equation. Now this further can give rise to d square by dx square of, instead of mg I can substitute EIZZ d square delta y by dx square equal to qy. Okay, so these are the main equations we need in order to solve any boundary value problem of flexural members. Okay, now let's move into the problem for today. So let me write problem number one. So problem number one, we have been given with the beam and loading. So we have been given with the cantilever beam and the following UDL, uniformly distributed loading. Say it is 5 kilonewton per meter. Now the details has been given. The length of the beam is this L equal to 8 meters, and the cross section dimensions also given. This is made of wood, so the Young's modulus is given as 10 gigapascal. The cross sectional dimensions, the depth and the width ratio is given as 1.5. H by B is equal to 1.5, and particularly H is given as 600 mm. So B will be 600 divided by 1.5, which will be 400, right? So B equal to 400. What else? So yeah, this is what given, and the loading, as I told, it is 5 kN per meter. Now we have been asked multiple questions, right? So we'll solve one by one. So first question is, what is the magnitude of y component of reaction force Fy acting at the ends? So we need to find the magnitude of reaction forces, okay, at A and as well as B. By the way, here at B there is no support, so reaction force won't be there, but still zero. But we will find for reaction force at A. Okay, so let's begin. We'll start with the equilibrium equation. So this for first thing we need to understand what is Qy for our question. The loading. So this is Qy, right? This Qy. This Qy is nothing but in our question it is Qy equal to minus 5, right? 5 kilonewton per meter. So Qy value is a constant. It's everywhere it's same, right? Now, what equation we'll use so that we'll able to find the vertical reaction forces. So let me name this as one, equation number one, equation number two, equation number three, equation number four. So I'm going to use equation number one. Equation number one implies dvy by dx plus qy equal to 0. So this implies dvy by dx equal to minus qy. So dvy equal to minus qy dx. I'm doing integration on both sides, or the section from 0 to x, right? So let it be indefinite integral. So we'll have a constant of integration minus this qy is constant, so already it's minus, so it will become 5x plus c1, okay, some constant c1. So this is the expression, but still we need to find the value of c1 to make it complete. Now we know at x equal to 8, there is no reaction force. So it gives us a condition, boundary condition. So at x equal to 8 meters, my Vy is 0. So when we substitute this, 40 plus C1, so C1 will be minus 40. Right, so C1 is minus 40. Therefore, my updated expression for Vy is Vy of x is equal to 5x minus 40. Right. So now we need to find the reaction force. Reaction forces at x equal to 0. My vertical reaction force Vy of 0 equal to minus 40 kilonewton, right? So what does this minus represent here? We are getting an expression for shear force, so we have got here the negative shear force. So negative shear force means in our as per our sign convention, this is positive shear force, right? Right side upward and left side downward is say considered as positive shear force, and opposite of it is the negative shear force. Now we got negative shear force, which means left side upward and right side downward. So we are considering at x equals 0, which is a section at left side. So left side will be upward, right? Left side upward. So my reaction at A will be 40 kilonewton upward, right? Upward. Fine. Okay. Suppose if I got here positive shear force, I would have considered this, and I'm looking at the left side support, so it is downward. Okay, uh, right? And suppose if I'm looking at the right side support, by the way, here there is nothing like that. Suppose if I'm looking at RB, say, then if my shear force is negative, I would have considered the downward direction, right? Because my shear is negative, right? So that's it. So this is about a reaction at the support. RA is 0, RA is 40, and RB is 0, right? RB is 0, no need of doing, because looking at the question, we can simply say it's a cantilever beam. There is no reaction at, okay, A and B. Now, next, we need to find the moment value. So let's use bending moment expressions. We'll use equation number 2. So dmz by dx plus vy. Equation number 2 implies dmz by dx plus vy is equal to 0. Okay. So dmz by dx equal to minus vy. This vy is already we have 40 minus 5x. So dmg dx. So integrating on both sides, we'll get mg of x equal to 40 times x minus 5x square by 2 plus C2. Okay, C1 already I have used, so that's why I'm using a new constant C2. Now again we need to substitute the boundary condition in order to find the unknown. So the boundary condition, looking at this beam, what we can say, at x equal to 8 meters, that is at the free end, my moment value is 0, right? So at x equal to 8, mg of x equal to 0. So this implies 0 equal to 40 times 8 minus 5 into 64 divided by 2 plus C2. So this implies C2 equal to minus 320, 32 5 160 plus 160. So this is minus 160. So C2 also, C2 I'm getting minus 160. So substituting my updated equation of mg will be mg of x equal to 40x minus 5x square by 2 minus 160. Fine. Now I need to find the moment value at the support. So where is the support? Support is at x equal to 0. mg of x will be what? Minus 160, right? Kilonewton meter. Okay, it's in kilonewton meter, right? Because load was in kilonewton, and this 8 0 everything is in meters. So I'm using kilonewton meters. Fine. So this is about the reaction. At, this is the reaction and moment at support. Fine. Magnitude of reaction force is done. This is actually part B. Magnitude of moment at support. Right. Okay. Fine. This is using equilibrium equations, differential equation, and doing integration way. Directly, you can also do this problem. Like, just draw the free body diagram. When we draw the free body diagram, we have something like this. That is, we have a uniformly distributed loading here, and the internal forces, the reactions are exposed, right? So here there is RA, and there is some MA. Right. This RA is nothing but as per vertical force equilibrium. Directly, you can, instead of going for differentiation integration, directly you could have written it for the simple problem. So RA will be equal to phi into the total load, right? The total load. I'm doing that method also. So RA summation of Fi equal to 0. This is from the free body diagram. Let me draw this free body down. From free body diagram, Ra will be equal to this 8 meters. This is 5 kilonewton per meter. So it is 40 kilonewton. And summation of moment at A equal to 0 implies ME is equal to 5 into 8. Where it will act? It will act to the center. It's a 40, 44 is a 160. Now about the sign, negative sign, right? As per moment, by the way, I didn't explain you what does this negative means. This negative means hogging moment, right? As per sign convention for bending moment, positive bending moment means sagging curvature. This is positive, and negative means hogging curvature. Okay, both side, like left side clockwise, right side anti-clockwise. Right, this is positive sign convention for us, right? And opposite of it is the negative sign convention for us. Okay, fine. So this is directly we can write to B. Okay, and moving on to the next question, variation of the shear force. Yeah, our shear force diagram. Shear force diagram for the beam. Uh, how to find? We already have the expression for shear force. Say this is equation number 5. This is equation number 5. No, no, that's not the final equation. This is my final equation. So this is equation number 5 and equation number 6. So equation number 5, we have 5x minus 40. So it's a linear diagram. So Vy of x equal to 5x minus 40. So when we plot this, we are going to get a linear curve, right? A curve with a straight line, a first order curve. So, and I think we can easily plot it. Let me draw the beam first so that I can draw it just below it. Okay. At x equal to 0, my x starts from here. x and y, x equal to 0, I'm getting minus 40. What color we'll use for drawing? Yeah, okay. X equal to 0, it's minus 40. What was it? It is negative shear force. And as it increases, it reaches 0. It is straight line. This is 5x minus 40. Okay, this is minus 40, this is negative, this is minus 40, this is 0. At x equal to 8, it is 0. Fine. Yes. So this is shear force diagram for us. And now actually we can tell the shear force at any location. The maximum shear force here is how to find the maximum shear force. Maybe looking at the diagram, we can simply say, but if you want to do it with math, we'll find the derivative, maximum value, derivative, what it comes, 5. Yeah, so its a derivative is positive, so it's a monotonically increasing function, so it has a positive slope. So it's will take at the boundaries, right? So at x equal to 0 and x equal to 8. At x equal to 0, we are getting the 40 value. So absolute maxima, like if you want to find without magnitude, sorry, without sign, we just need the maximum value irrespective of positive or negative it is. So we will get a value of 40 kilonewtons, right? That's maximum at x equal to 0. Hmm? And moving on to the bending moment diagram, that's our next question. Question number D. Ask us to draw bending moment diagram. How to draw a bending moment diagram? We already have the profile of bending moment, mz, where it is equation number 6. So equation numbers, this is equation number 5. Equation number 5 implies, so equation number 6 implies mg of x equal to 40x by x square by 2 minus 160. Right. So when we draw this, we are going to get a quadratic equation. Right. So let's just plot this. Maybe I can move this a little up so that I'll plot it just below the shear force. Yeah. So let's plot bending moment diagram. Now at x equal to 0, the value is minus 160. Okay. And x equal to 8, it is 0. And the curve is a quadratic curve. So we can get two possibilities. This is possibility number 1. Let me draw it a little more mm, legible. This is possibility number 1. Or we can also get possibility like this. Like what? Like this. Which one is correct? First one or second one? Both are quadratic curve. Both satisfies the boundary values. Now the curvature are different. In one, slope here is 0, and another one, slope here is 0. How to find which one is correct? We know this relation, which relation this relation between the moment and shear. Equation number 2, dm by dx plus vy equal to 0. dm by by dx plus vy equal to 0, which says that shear force is nothing but the slope of bending moment diagram, right? So here the slope is 0, here the slope is 0. So how to find which one is correct? Hmm? Where That's correct. Yeah, where the shear force becomes 0, their slope must be 0, right? In a shear force diagram, see here my slope is 0. Sorry, value is 0. So this is wrong. This should be correct. Fine. So this is my correct bending moment diagram. So here value is 160, right? Yeah, negative 160, and their value is 0, and this is the quadratic curve, 40x minus 5x square by 2 minus 160. Right, this is my bending moment diagram. This is wrong. Fine. So this is the variation of bending moment. Now, if you want to find where the maximum bending moment is, it's really evident from the diagram, but still, if you want to go with math, dm by dx equal to 0. This implies 40 minus 5x equal to 0. We are getting 5x equal to 40, x equal to 8. X equal to 8. By the way, here dm by dx is 40 minus 5x. So at x equal to 0, my dm by dx is positive. At x equal to 8, my dm by dx is 0, right? So it is again a monotonous function. It is again a monotonous increasing function because slope is positive. It is increasing, yeah. So maximum value, if you want, again we'll check at the boundaries. So at x equal to 8 and x equal to 0. So at x equal to 8, when we substitute, we will get 0. At x equal to 0, when we substitute, we will get minus 160. Yeah, but we need absolute maximum. So the maximum magnitude value is minus 160, which occurs at x equal to 0 itself. Right, so bending moment maximum is 160 kilonewton meter, which this occurs at support A, right? Support A with hogging. Okay, it's hogging, negative. So this is subdivisions D. Okay, so far good. Next, location of maximum. Yeah, this all we have done. Location of maximum bending moment from A. Again, we have done. And What else? Magnitude of maximum bending moment also we have done. Location of maximum shear force also we have done at support, and magnitude of maximum shear force also we have done. Okay, this we have completed that. Next is value of shear force at the location of. Okay, again for this question it's same. Next, we are moving on to stresses. So this is force response. The force, bending moment, shear force and bending moment. Now we'll see about the stresses. The bending normal stress value, the maximum shear stress value. The next part is E part, the uh, magnitude of maximum bending normal stress. The magnitude of maximum bending normal stress. How to find the bending normal stress? The bending normal stress equation is equation number 3. So minus sigma xx by y minus y naught equal to, I'll take the first two terms since we have the bending moment. So equation number 2, right? 2 implies sigma negative of sigma xx by y minus y naught is equal to m by I. Right. So equation number not 2, 3 minus sigma by y means not equal to mz by izz. Equation number 3. Now substitute here. So this implies minus sigma xx by y minus y naught. Y naught is 0 because here we are fixing the origin at the centroidal axis. So it is 0 minus equal to mg is what? Mg, we have the expression already. By the way, all this is true only when 0 to 8. Okay, these expressions are true only for the regions inside the beam. So mg is what? 40x minus 5 by 2 x square minus 160. Izz, Izz we have to find based on the section properties. What is B? What is D? B is 400, D is 600. So Izz will be 400 into 600 cube BDQ by 12. Let me use a calculator. 400 into 600 cube by 12. 10.2 into 10 to the power 9. Yeah, mm per 4. Okay, stress, by the way, we need in megapascal. Uh, we are asked to find in megapascal. So it's better to convert everything in terms of Newton and mm, so that it is easy. Substitute it back. Okay. By the way, we want maximum value of the bending normal stress. So it depends on where my bending moment is maximum and the maximum value of bending moment. So here in this question, we have the bending moment as the maximum bending moment as 160. So it's negative 160. So sigma xx equal to negative 160, negative cancel, kilonewton meters into 10 power 6 Newton mm, right? Newton mm, m by, this is 10.2 into 10 power 9 mm 4, right? Into y. Y is what? Y is the distance of the extreme fiber. Why extreme fiber? Because we want the maximum value. Okay. For maximum or minimum value, we need to go the extreme fiber for bending normal stress. So here, since it's a rectangular section, the neutral axis will be at 600 by 2, which is 300 mm. Okay. So finally, we'll get the answer in Newton per mm square. 300 into 160 into 10 to the power 6 divided by 7.2 into 10 to the power 9. We are getting 6.67 megapascal or Newton per mm square. Okay. This is my bending normal stress maximum. Now, if you want to find the variation of bending normal stress, we can do at the not midspan, at the section where my bending moment is maximum. Yeah, it's going to look like sigma xx equal to, this is m's value into y by I. Okay, it's a function of y. Y is the depth value. So it's going to be a linear straight line. Okay. At top, it will be in compression or tension. Like when we find sigma xx, my mz is negative, y naught is 0, so it's negative. This is, so y will be positive. At top, my y will be positive. So therefore sigma xx will be positive. Okay, so I'm going to get the variation as like this. This is positive. And at bottom, my y is negative. My sigma xx will be at bottom. Sigma xx will be negative. Right. So when we join this, we are going to get a variation like this. So positive means tension, tensile stress. Negative means compressive stress. Right. So this is Yeah, because it's a cantilever, so it's going to show a hogging curvature. A hogging curvature means in the top fiber, it's going to be elongate. In the bottom fiber, it's going to get contract, right? So above it's positive, below it's negative. Next question is what maximum value of shear stress. Subdivision number F. The maximum shear stress. How to find the maximum shear stress? We know the shear stress formula is tau is equal to VQ by I B. This is sigma XY is equal to Vy IZZB. Hmm? So this is my formula where Q is nothing but area into moment of inertia, area moment of inertia about the section where we need to find the shear force, horizontal shear force. B is nothing but the width of the section where we are interested in. So when we do this for a rectangular section, we will finally end up in sig tau equal to tau max is equal to 3 by 2 times the average shear force V by A. So this is for a rectangular cross section. We have already derived this. You can check it out. Okay. So 3 by 2 into V by A. What is V? The maximum value of shear 40. 40 kilonewton by area. 400 into 600. Okay. So 20 sa 0, 1000, so 1, 2, 3, 4, right? What else is there? 3, 2 sa 6. So 1 by 4 is there. It's just 0.25 megapascal. Okay, shear stress. Fine. Now, if you want the variation, again, tau equal to V is constant, I is constant, B is constant, Q is going to vary. Q is nothing but the area moment of inertia. So we will get a parabolic variation with 0 at the boundaries, the top and bottom, and maximum at the center. Right. So it's going to look something like this: 0, 0, and here is maximum. Okay, here this maximum is 0.25. Now, yeah, moving on. The next question is, yeah, this finishes the stresses. Then is the deflection. Subdivision number F G. Deflection uh, in the beam. Now, how to find the deflection? We need to use the basic differential equation and do integration. Okay, that's the way double integration method we call. We can use equation number 4 or equation number 3 also in the bending equation. I'm going to use equation number 3. The EIMZ equal to EIZZ d square delta y by dx square. That implies d square delta y by dx square equal to m v by e I z z. So integrating on both sides, we'll get d delta y by dx equal to mz is what? Mz of x, this term 40x minus 5 by 2x square minus 160. Okay, so this is divided by e into maybe value we'll substitute at the end. No need to do it now. Just checking is my value, right, 40x minus 5x square minus 16. Yes. So this implies we can do integration. So now d delta y by dx equal to 1 by e I z z 40x square by 2, 5x by 3 by 3, 160x plus C3. Okay, C1, C2 already I have used, so I am going to use another constant, that is C3. Now further, one more time when we differentiate delta y of x, okay, equal to 1 by I z z 20 20x cube by 3 minus 5x power 4 by 24 minus 160 x square by 2 plus C3x plus C4, a new constant. Now our aim is to find these two constant, uh, which is C3 and C4. Now we'll use boundary conditions in order to find these two. What are the boundary conditions from this question for deflection? So at reaction at support A, it's a fixed support, which means my, let me move this away. Yeah, which means my deflection and slope will be 0. Yeah, at x equals 0, my delta y of x would be 0. So this implies C4 will be 0. Good? It's, it's good. And what is the another condition? At x equal to 0, again my slope is 0. d delta y by dx of x 0. This implies C3 also will become 0, right? E delta y is here, so yeah. So my final expression, the updated expression for deflection and rotation is d delta y by dx of x is equal to 1 by EIGG times 20x square. Okay, that's it. Now we need to find the maximum value of deflection. Okay, cantilever beam, it's going to deflect with the maximum value at the free end, right? That we know. Yeah, at B, we are going to get the maximum value of the deflection. Suppose if we are not convinced, no worries, we can simply use math to find that that is the point where maximum deflection occurs. We can use the derivative, find the minima, maxima, absolute and local extremum values. So finally, we can able to get the maximum value in the of the following function, deflection function in the given domain from A to B. Right. So I am going to substitute directly x equal to 8. So at x equal to 8, delta y of x equal to 1 by EIZZ. So let's use calculator to solve this. 20 by 3 minus 5 into 64 square divided by 5 divided by 24. 20 into 512 by 3 minus 5 into 64 square by 24. Okay. And minus 80 into 60. I'm getting 1 by E is 10 gigapascal. I is how much high we got? 7.2 into 10 power 9. into these things, I'm getting minus 2560. Okay. So, by the way, one is in meters, another is in millimeters. So they need to be consistent. So this thing is Newton mm square. This thing is kilonewton meter, right? That is. So this has to be multiplied with 10 power 3 into 10 power 3. Okay. So units, we need to be a little cautious here. Just a minute. Let me recheck once. So this is the expression for deflection that we got. So E Newton per mm square times I is in mm per 4. So Newton mm square into this mz that we substituted is in kilonewton meter. Yeah. So I'm going to multiply here into 10 power 6. Why 10 power 6? Because for kilonewton and meter. So this will be into 10 power 6. Okay. So finally we'll get 2560 into 10 power 6 divided by 10 power 9, 10 power 3, 10 power 12, 10 power into 72. 72 into 10 power 12. Okay. I'm getting very, very, very less. Minus 3.56 into 10 power minus 5 mm. Okay. Fine. This is the value I'm getting. So here the important thing is, what is this negative sign represent? The negative sign represent the deflection is downward. Okay. Next, what is the magnitude of the rotation at the end A and B? So next subdivision, H, rotation at fixed end A in clockwise direction they are asking. Okay. Rotation is this formula, like this equation in here. So this I'll just put a duplicate and I'll copy it here. So this is my rotation. So at x equal to 0, my rotation at A It's okay, this they are also asking in B, A and B. So at x equals 0, my d delta y by dx will become 0. It's okay, 0 degrees. They are asking in degrees, and similarly at x equal to 8 meters, d delta y by dx will become 1 by EI is 10 into 10 power 3 Newton per mm square. This I was 7.2 into 10 power 9 mm power 4. 7.2 into 10 to the power 9 mm power 4 EI times 20. Okay, I think, yeah, let me substitute here directly the value of x in mm. So x is, because yeah, that's why in the previous subdivision the value was very less. Here it goes x square and x cube, but we have only done 10 power 3. Okay, so that is a mistake. 8,000 square minus 5 by 6, 8,000 cube minus 160 into 8,000. Okay, 8 meters I am substituting in terms of millimeters. So this will be little careful. We have to do 20 into 8,000 square minus 5 by 6 into 8,000 cube minus minus oh oh oh, what to do? Yeah, I have to do from beginning. 20 into 8,000 square minus 5 by 6 into 8,000 cube minus 160 times 8,000. Okay, this divided by is a big number going on here. 10 power 3, 10 power 9, 10 power 12, 72 into 10 power 12, 72 into 10 to the power 1. So this is minus 0.00591 radians. I want in terms of degree. So this multiply by 180 by pi. This multiply by 180 divided by pi. So I'm getting negative 0.3439 degrees. Okay, this is what I'm getting. Okay, let's go back to the previous thing and let's erase this and let's resolve it again. So equation of deflection implies delta y of x is equal to 1 by EI is 10 power, this is 72 into 10 power 12, right? 72 into 10 power 12 times 20 into x is 8 meters. So 8,000 millimeters by 3 minus 5 by 24 into 8,000 per 4 minus 80 into 8,000 square. So this implies let's do 20 into 8,000 cube by 3 minus 80 into 8,000 square minus 5 by 24 into 8,000 per foot. Okay, divided by 72 into 10 power 12. So I'm getting minus 11.8 mm. Yeah, so the negative sign implies it's downward. Okay, that's it. And here the negative sign implies it says clockwise. Since the question they are directly asking for clockwise, so we can simply say this rotation as 0.3, if round off to 2 degree, 2 decimal place means 0.34 degrees. Okay, so that's it. Fine. So this finishes the first problem that I have for today. So we have seen how to calculate the reactions, the shear force, the bending moment, the bending normal stress and shear stress, finally the deflection and the rotation. Okay. Square by 2 plus
Let's
C1.
move on with the second problem for the
Okay.
day.
So
So in the
boundary
second
condition.
problem, instead of a cantilever beam, a simply supported beam is given here. And instead of a UD, we have a simply supported beam, not a cantilever beam. And we have been given with a UVL, uniformly varying load. Okay, so this is 2 and this is 5. That's the only difference. And the coordinate system also changed here. So this is my Z, this is my X, and this is my Y. Okay, so we have to be careful with the terms that we are going to use. Okay, so MZ will become MX, and it will be swapped with whatever derivation that we have derived. Okay, so we have to be a little cautious there. And the other properties are same. That is, H is equal to 600 mm, B is equal to 400 mm, so that H by B is equal to 1.5. And similarly, this would, so 10 gigapascal. This I'll say 10 into 10 power 3 megapascal. Okay. Right. So this is given in the question. Now it's time for us to solve the problem. So let's go one by one. First, let's finish off the shear force bending moment with the reaction at the support. So reactions. Now, what is W here, by the way? This is not a constant W. It's a linearly varying W, right? In the previous question, the W was constant. So here the W is varying. I don't know what it is. So let me write AX plus B. So at X equals 0, my W is given as 5 kilonewton per meter. So that implies 5. It's minus 5, right? Minus 5. Minus 5 equal to B. And at x equal to 8 meters, w equal to 2 minus 2. So this implies this equation number 2.1 say equation number 2.1, that implies minus 2 equal to a into 8 minus 5. 8a is minus 5 equal to minus 2. 8a equal to 3. Okay, so a equal to 3 by 8. So my actual loading W is 3 by 8 x minus 5. Okay, this is my real load. Fine. We can check it at x equal to 0, it is minus 5, and x equal to 8, it is minus 2. Right, so this is my W given. Now I'll do with the differential equation method. Okay, that is d v y, this equation number 1, dvy by dx plus qy equal to 0. So this implies zero. This qy is nothing but this w. Okay, this implies 5 minus 3 by 8x. This implies vy equal to x minus we have been given with a UVL. Okay, at x equal to 0, at A the load is 5 kilonewton per meter, and it is linearly varying, reducing it to 2 kilonewton per meter at the other support. Okay, and there is another change in the question here. If we look carefully, this is not the coordinate system that we adopted to derive our equilibrium equations. So there is a change here that we need to be careful about. Okay, so apart from that, all the other questions are moreover the same, which is asked as previous. So let me just rewrite the equilibrium equations so that we'll be able to do it properly. Okay, so now this dmx by dz, okay, plus actually initially it was dmz by dx plus vy equal to 0. Now this becomes dmx by dz plus vy is same because it is not changing. Only x and y are swapped. My longitudinal axis is x-axis, which was assumed before. Now z-axis became a longitudinal axis and x-axis became a transverse axis. And there was another equation we had, dvy by dx plus qy equal to 0. This now becomes dvy by z plus qy equal to 0. Okay, so these are my new equations. And the bending stress equation, minus sigma zz by y minus y naught equal to m, z become mx by izz become ixx equal to e into d square delta y by dx dz square. Right. So these are my new set of equation for this particular coordinate system. Okay. Right. Let's proceed. First, what is qy in this problem? In the previous problem where we had UDL, qy was a constant, but here qy it's changing at each point linearly. So first we need to find a proper expression for qy. That's the first step. Okay. So finding qy. So how qi will vary? Here in this problem it's linear. So let me assume qi equal to some ax plus b, some a and b are some constant, so some linear function. Now this implies, and at x equal to, oh sorry, it is z, a z plus c. Let me use this letter for z, az plus b. At z equal to 0, qy equal to what? Minus 5, right? 5 kilonewton per meter. So this implies my b will become minus 5. Okay. And at z equal to 8, my qy will be minus 2. So this implies minus 2 is equal to a into 8 minus 5. So this implies 5 minus 2 is 3 by 8 is a. So now therefore my qy of z will be 3 by 8z minus 5. Okay. This is my expression for qy. Fine. Right. So let's now proceed. First we need to find the reactions and the shear force, bending moment. Yeah. So that is stress resultant. So we know there is an expression, this equation letting shear and bending, that is dv not shear and the load, the dvy by dz plus qy equal to 0. So this implies dvy by dz equal to minus qy. Right. So this implies dvy by dz equal to 5 minus 3z by 8. Okay. So this implies vy equal to 5z minus 3z square by 16 plus c1. Right. So this is Vy, and moving on to the second equation, that is dmx by dz plus Vy is equal to 0. So this implies dmx by dz equal to minus Vy, which is 3z square by 16 minus 5z minus c1, right? Now AMX of Z will be integrating on both sides. ZQ by 3 will go 16 minus 5 Z square by 2 minus C1Z plus C2, right? Now let's apply the boundary condition. What are the boundary condition? This is a simply supported beam. So at at Z equal to 0, my mx of z will be 0. Similarly, at z equal to 8, my mx of z will be 0. So this first boundary condition will give us C2 is equal to 0, right? Second boundary condition, if we substitute 0 equal to it's a 16, 64, it's a 512 by 16 minus 8 a 64, 5 into 64 by 2 minus 8C1. So this implies 0 equal to 2 ones are 32 sir, 2 8s are 256 sir, 8 ones are 8 32 sir. Okay, so 32 minus 5 times 32 equal to 8C1. 8C1. Now C1 will be 4 minus 5 times 4, which is 4 times 4 minus 16. Okay, C1 is minus 16. Now my bending moment expression will become, the updated equation will become mx of z will be zq by 16 minus 5 z square by 2 minus of minus plus 16z plus 0. Okay, so this is my bending moment expression. And also shear force also we can get. Shear force expression will be Vy equal to Vy of z equal to 5z minus 3z square by 16, 3z square by 16 plus C1 is minus 16. Okay, fine. And what is the domain of z? Z varies from 0 to 8. Okay, only within this domain it is true. After that, it's not true. Right? That's the domain we have. Fine. Now what about the reactions? Now if you will do reactions. No, at z equal to 0, my Vy of 0 will be minus 16. Okay, kilonewton. Minus 16 means what? Shear force is negative. So negative shear force means left side upward, right side downward. This is my negative shear force means. So at A, my section is at left side. So my reaction will be upward. Okay, upward. 16. And at Z equal to 8, Vy of 8 will be equal to 40 minus 3 into 8 is 64, 16 minus 16, 4 equal to 40 minus 12 minus 16. So this will be 16, 26, 28, 38, 12 kilonewton. So this is Vy of 8, and this is at right. Positive shear force again means upward. Okay, my positive shear force convention is this. I am looking at a right side section at B. So this will be my direction, that is upward. Okay. So this is all about reaction, and we know moment at A and moment at B is zero. Okay, this is using equilibrium, the differential equations. The same thing actually we could have done using the free body diagram, okay, without doing any of these differential calculations or integrations. Directly we would have got using free body. Let me just quickly illustrate that. Let me copy this, duplicate. Come down, come down, come down. Yes. Yeah. This was my question. So how about my free body? Can we draw the free body? Yes, we can. So this is my beam body. Looks like AB. And what are those reactions? The reactions are, there is a reaction RA, there is a reaction RB, and there is some loading. The loading is UBL. Okay, this is another method I'm writing instead of going for this differential equations. For finding support reaction, I'm just going to use directly free body. Okay, so summation of Fi equal to 0 implies what? Ra plus Rb will be equal to, this is 2, this is 5, na? 5 kilonewton per meter, this is 2 kilonewton per meter. So total load is the area of this trapezium, half into A plus B into H. H is 8. So this is equal to 4, 7 are 28. Okay, total load is 28. RA plus RB. Next, maybe moment at A can we do? Moment at A equal to 0. This is upward positive. And let me take anti-clockwise positive. So this implies RA in RB into 8 will be equal to, again here it's a trapezoidal loading, so I'm going to break down into two loadings, that is a triangular loading and a rectangular loading. Okay, this triangular 0, and I guess it is 5 minus, okay, this is like that. Yeah, 5 minus 2 is 3, and a trapezoidal load, a rectangular loading. 2, 2. Okay. So this will give moment. Okay. This will act here at 8 by 3, B by 3, and this will act here at 8 by 2. Okay, B by 2. Now, this will be equal to area of the green. Okay, half into base into height times distance is 8 by 3. Okay, this is the moment. Which direction? Which is yeah, opposite to B. Right. So it is, I'm writing on the equal clockwise moment equal to anti-clockwise moment. Okay, this plus one more we have. I use this color. That is, area is 2 into 8, and this is 8 by 2. Okay, now this will give rise to 3 will get cancelled. 64 by 2 is 32 plus 2 to cancel, 8 8s are 64. So RB will be 4 plus 8, which is 12. Okay, 12. I'm getting positive, so my assumed direction is right. And so using the equation here, RA plus RB equal to 28, so RA will be 16. Okay, same answer. Okay, that we got before. Both are upwards. Right. Here also we got the same, na? 16 and 12. 16 and 12. Correct. Okay, so this is a direct way of deriving. Right. Now, let's move on to the next question, that is the shear force and bending moment diagrams. Shear force and bending moment diagrams. Already we have the expression for both shear force diagram and bending moment diagram. It tells us the variation of shear force and bending moment over the span, over the longitudinal direction, right? Z direction. Now, this is the question. So, we have the expression for shear force, right? Where it is, yeah, here it is. Let me copy this, duplicate. Okay, this is the expression. Now, yeah, we can find where it is maximum, where it is zero, everything. So, to finding maximum, so that for finding maxima, values, we get dm x by dz equal to 0. This implies 3z square by 16 minus 10z by 2 plus 16 equal to 0. Okay. This implies 3z square multiplied by 16, 2 ones are 2 8s are, so 80z plus 16 is 296 equal to 0. Okay, so now we need to solve for this quadratic equation. Sixteen square is two. Oh, yeah, sorry, here it's 256. Quadratic equation, let's take quadratic equation solver. So ax square plus bx plus c, this is 3, this is minus 80, and that is 256, right? So we have two roots here. Z is equal to 3.718 meters and Z equal to 22.95 meters. So two roots. Okay, and since Z can be vary only from 0 to 8, this is not possible. So this is our answer. Fine, this is our answer where my moment is maximum. Okay. Right. Can we find the maximum value as well? Yes. We'll just substitute at z equal to 3.718 m z m x of z equal to 3.718 cube by 16 minus 5 into 3.718 square by 2 plus 16 into 3.718. So this implies 3.718 cube by 16 minus 2.5 into 3.718 square plus 16 into 3.718. So this is equal to 28.14 kilonewton meters. Okay, positive moment which is sagging. Yeah, of course, in simply supported, the beam is going to sag. So positive moment I am getting the maximum value. Okay. Now, can you find the maximum of shear force? For maximum of shear force, of course, shear force is going to be maximum at the supports, right? Let's see, anyhow with the expression dv by dz equal to 0, that implies dvy by dz equals 0, that implies phi minus 3 twos are 6 z by 16 equal to 0. So phi equal to 6z by 16, z equal to 1680 by 6, which is more than, right? So it's going out. There's a maxima or minima outside the wound. Okay. Which we are not interested in, so not required. So it is some monotonous function. Sorry. By the way, can we find, is there any place where my shear is getting 0? Because we have a maximum value of bending moment. So at that point, the slope will be 0. So my shear force will become 0. So if I substitute Vy of z equal to 0, this implies phi z is phi z minus 3z square by 16 minus 16 equal to 0. So this implies 80z minus 3z square minus 256 equal to 0. So I'm getting two values again. Quadratic equation. So A is minus 3, B is 80, and C is, so it's the same. So wherever my bending moment is maximum, there the shear force is 0, right? It's the same expression. I also forgot, right? Because V by dx is, sorry, dm by dz is nothing but v. Okay, already we equated that to 0. Again we are doing the same by equating the shear force to 0. Both are same expression. Okay, so wherever my bending moment is maximum, there shear force will become 0. Okay, means, see, in the last problem, it was not the case, because there it is not like absolute maximum, right? We had a monotonous function, but here we have something like this. It goes and change the curvature sign, right? We have a decreasing and then increasing function, right? So for these cases, wherever my bending moment changes, attains a maximum value, there shear force changes sign. Okay, this is important property that we need to know. Now let's draw the diagrams. Okay, we have everything. So let's draw the diagram. So this is the proper expression we can plot, but it's a cubic function for bending moment and a quadratic function for shear force. It's always the case if loading is linear. Sorry, I have to change the screen. Sorry. Yeah, if loading is linear, always the bending moment, the shear force will be a quadratic and the bending moment will be cubic. Okay, this is always the case. Now, can we just draw? Yes. So This is my beam, say. At A, my shear forces. Where is the shear force at A? We got minus 16, and shear force at B is plus 12. So at A, it's minus 16. Minus 16, this is plus 12. And it is becoming 0 at, becoming 0 at 3 point, how many, how much? 3.718. 3.78, right? So it's before midpoint, okay? Right? And I'm going to draw this cubic function. And is it flat here? No, because loading is not 0. Okay, so this is, assume it is a cubic function given by the expression in here. Okay, this expression. And next, sorry, it's a quadratic function, not a cubic. Bending moment is cubic, no? This is quadratic. Okay, this is shear force. Next, bending moment diagram will look something like this. So both the support, it's 0, and it's attaining maximum here. At this point, it is maximum. Okay, the maximum value is given by 28.14. 28.14. This is a cubic function. Okay, this is BMD. Right. Next, moving on to stresses. So we need to find the bending normal, maximum bending normal stress. Normal stress, maximum value, and maximum shear stress value. So maximum bending stress will be that sigma xx, right? Sigma xx by y minus y naught. Y naught is 0. So this is equal to m by I. This by y equal to this minus ym xx mx by I z xx. Okay. So this implies sigma, I want maximum value, sigma xx max. Is it xx or zz? It is zz. Okay. Because it's my longitudinal flux. Sigma zz max will be minus mx is max is 28.14 kilonewton meter, so into 10 power 6 divided by I is same what we have from the previous question. What is the value of I? 7.2 into 10 power 9 mm per 4. So 7.2 into 10 power 9 mm per 4 into y. Okay. Now for finding maximum, y will be at the extreme fiber, right? So at one fiber there will be a positive, another fiber there will be a negative, right? Here at top fiber, my y will be d by 2. What is the d? Forgot. What is the d given in the question? D was 600, or H was 600 mm, the depth. So 600 by 2 will be 300. Top fiber, it will be 300 mm. Okay. So sigma ZZ max value will be minus 28.14 into 10 power 6 into 300 divided by 7.2 into 10 power 9. This will be this 10 power 6, 7, 8, 10 power 9. This into 3 by 72 into 3 by 72, getting 1.173 megapascal. Okay. And similarly at bottom fiber, y equal to minus 300. So sigma ZZ max will be plus 1.173 megapascal. Okay, this is tensile. This is compressive, right? Compressive. Okay. So this is the maximum value of bending normal stress. Next, let's find out what is the maximum value of shear stress. Shear stress maximum. Okay. Actually, tau, the formula for shear stress was tau equal to V U by I B, right? Now, if we do the computation and for a rectangular section, I can write this as tau max equal to 3/3 of average shear stress. Okay, so this is equal to 3 by 2 times what was the maximum shear? V max is, I guess it's 12, no? 16, yeah, 16. 16 into 10 power 3 newtons by area of cross section is 600 times 400, right? So 10 power 3 is there, 1, 2, 3 are gone, 4 ones are, 4 fours are, 3 ones are, 3 twos are, 2, 2, 4. So it became 1 megapascal. Okay. Tau max is 1 megapascal. Fine. Moving on. Next, we need to find the deflection and the rotation. Deflection and rotation at support. At support, also maximum deflection. Okay, maximum deflection equal to what? Right. So let's use the differential equations connecting the moment and the deflection. Where is it? Yeah. Okay, this bending equation, when I substitute here inside, I'm going to get what instead of m, I can write ei into d square y by dx square. So that is m x equal to e I x x d square delta y by d z square. Okay, right. So this implies d square delta y by dz square equal to m by mx of z by ei xx. So this implies d square delta y by dz square equal to 1 by ei xx. What is the mx of z? Mx of z is, here it is. Let's copy this. Yeah. Well, the pasted image went. Oh, didn't paste it. There are no image. Okay. Let me just duplicate. There's some issue. Seems like. For this time, I would have written this equation. Okay. Anyways. Finally, we have got this. Okay, so 1 by EI into Z cube by 16 minus 5Z square by 2 plus 16Z. Fine. I hope this is right, no? This implies what we do? Yeah, we'll integrate. So d delta y by dz equal to 1 by ei xx times z power 4 by 64 minus 5 z cube by 6 16 z square by 2 plus e1. Okay. C1, let me take it outside so that z square. Hmm? Okay. Right. Now again differentiating delta y of 3 now will be 1 by ei xx times z power 5 by 64 times 5 minus 5 z power 4 by 6 4s are 24 plus 8 z power 3 by 3 plus C1z plus C2. Now, what is the boundary condition for simply supported beam? The boundary conditions are at both the supports at x z equal to 0, deflection will be 0. Right. So this implies C2 equal to 0. And what are the other boundary condition? At z equal to 0, z equal to 8, the other side, z y of delta y of z will be 0. So this implies 0 equal to 1 by ei xx z power 5, no, z is 8, no, I have to substitute, so 8 power 5 by 320 minus 5 into 8 power 4 by 24 plus 8 power 4 by 3 plus 8c1. So we get this is again 8 is in meters. I should have taken this in mm. So what to do? We have to convert this, right? So let me compute in terms of mm itself. Let me write this once again. Xx 8000 per 5 by 320 minus 5 into 8000 per 4 by 24 plus 8000 per 4 by 3 plus 8000 C1. So EI values is 10 into 10 power 3. I is 7.2 into 10 power 9, right? If I remember correctly. 7.2 into 10 power 9. Right. So this will be, we have to simplify this. 8000 into 8000 power 5 divided by 320 minus 5 into 8000 power 4 by 24 plus 8000 power 4 by 3. Oh, it's a very, very huge number. Divided by 10 power 9, 10 power 10, 10 power 13, 72 into 10 power 12. 72 into 10 power 12. So this itself I'm getting 1429.3 plus 8000 C1 is equal to 0. So C1 will be just by 8000. Just minus 0.179. Okay, done. So we now got the deflection equation as well as the rotation equation. Now we need to find the deflection at the maximum deflection. Also, we need to find the slope. So we know at maximum, for maximum deflection, my d delta y by dx must be equal to 0, right? So this implies, if I equate this thing here to 0, so what I'll get, 1 by EI is 72 into 10 power 12. Na? Every time I'm writing big expanding. So 1 by EI. This is what I'm writing into Z. Okay, so fourth order equation. 1 by EI. Z power 4 by 64 minus 5Z cube by 6 plus 16Z square by, that is 8Z square plus or minus 0.179 equal to 0. Okay. Right. So how to solve this equation? Set for 4 looks like numbers are not right. Let's do 5Z cube by 6, 8Z square equal to 0.179 into 72 into 10 power 12. So Let's solve this. I think we have a fourth order equation solver, fourth degree equation calculator. I got it. One. Where is to compute? Okay, I think simply I'll change and see how to compute. I don't know. Here, I don't think it is computing. No. What equation calculator? Yeah, here there's one. So 1 by 64 into x power 4 minus 5 by 6, 5 by 6 into x cubed plus 8 x square minus 72 into 10 power 12. It look crazy. Haha. 0.179. Oh, let's see what it gives. It's giving us some answer. Yes. So there, out of the four routes, I'm getting 5 point, make some sense, 372 meters. Okay, other three are not applicable. Two are imaginary, one is negative. Okay, so this actually solves the thing. So yeah, of course, it's near the midspan, not exactly the midspan since the load is not symmetric. So maximum delta y max will be at this value. Let's calculate it back. Where is the deflection expression? The deflection expression is, yeah, here. Okay, yeah, here it is. So in this we have to, so shoot. I'm just keeping it here so that no need to scroll each and every time. 72 into 10 power 12 times 5.372 power 5 divided by 320 minus 5 into 5.372 power 4 24 plus 8 into 5.372 power 3 by 3 plus C1Z. C1 was minus 0.179. Minus 0.179 into 5.372. Okay, so this will give us the value in mm. Oh, meters. Okay, this is then not decimal. I want in mm. Yeah, no more. Yes, we can proceed. So, 5372 power 5 divided by 320, very big number, minus 5 into 5372 power 4 by 24 plus 8 into 5372 power 3 by 3. Yes. This divided by 72 into 10 power 12. Okay, it became 191.773 minus 0.179 times 5372. 961.59. So this gives us 769.8. It's a big number. I'm getting this much mm. Okay. So this is delta y max I'm getting downwards. Okay. And similarly for rotation at the support, we have an expression here d delta y by dx here. In this, if we substitute z equal to 0, we will get c1. So directly c1 is the rotation at support A, and if we substitute z equal to 8, we will get the rotation at B, right? So fine. So I think we are running short of time, so I am stopping it here. So this is how we solve this problem, and we have one more problem to go. Here we have been given with, I'll just quickly illustrate how to do problem number 3. We have been given with a built-up I section having width of the flange 500 mm and thickness of the flange 10 mm, depth of the web 600 mm, thickness of the flange 10 mm. There's some I section given. And this here there is a weld, okay, at this interface between the flange and the web. There is a weld and there is a shear force of 1 kilonewton applied. I section is built up by welding the web with the flange. Find the shear stress that the weld should withstand. Okay, shear stress at the interface equal to what? Okay, so directly we know that tau shear stress equal to VQ by IB. Nah. So moment says this is X, Y, it is Z, Vy. Right. So here Vy is straightforward. IZZ alone we have to find. IZZ equal to, we can find this. So this is 500, this is 10, this is TF is 10, and this is 600, right? So how to find ICC? There are two methods. First method, we can consider this as three rectangles and find, okay, using parallel axis theorem, or we can extrude, I assume it's a bigger triangle, 500 into 600 plus 20, 620 cube by 12 minus just the exploding portion. So 500 minus 10 is 490 into 600 cube by 12. Okay, this is I value. What is Q value? Q is nothing but the area into the centroid. Okay, here this is my region. Okay, where I'm where which will contribute to this Q. So area of that is 500 times 10 times 5. Okay, this is Q. Okay, what is B? B is the width at the interface, that is 10, thickness of the web. Mm. Okay, all these things is in mm cube, power 4. What else? Vy is in 1000 newtons. Now, when we substitute this, we will end up with the final value of the shear stress, right? Vy into Q into ICZ into B. Okay, let me quickly do it and give you the numbers. 1000 into 5000 into 5 is 25,000 divided by, oh, we need I, right? Yeah, let's calculate then. This I will become 500 into 620 cube minus 490 into 600 cube divided by 12. I became 1.11 into 10 power 2, 3, 4, 5, 6, 7, 8, 9. 9 power 4. So this into B is 10, reciprocal of it, times 1000 times 25,000. Okay. So this much into, maybe I'll write in kilopascal, 2.225 kilopascal. Okay, it's low, but yeah, that's what we get. Fine. Right, so I think with this I'll stop for today. So I'll just quickly recap whatever we have seen so far. First, we started with how to solve a boundary value problem related to flexural members. Flexural members are members which are subjected to load, a transverse load that will cause bending in the member, right? It's going to produce the deflection and the rotations, right? And we saw these are the basic equilibrium equations that will help us to solve the problems. And using compatibility, strain displacement, we got this bending equation. And yeah, so moving forward, like we saw how to solve a problem, right? We saw how to find support reactions, how to draw bending moment diagrams, how to draw shear force diagrams, and we saw how to calculate the normal stresses, bending normal stresses, maximum shear stress. Also, how to find the deflections and the rotations using the proper boundary conditions. Okay. And also we saw for the case of UBL, and there is a change in the loading value which is linear, right? So that's what we saw. Fine. Right. Thank you very much. So with this, I'll stop for today. We'll see again in the 8th week. Right. Thank you. Thank you very much. Bye.